Thank you so much, Randy. I'm going to get started with this presentation with a simulation that I'd like everyone to actually do at your offices. I want you guys to get out a sheet of paper or a Microsoft Word document, and I'm going to give you a scenario that I want you to address on the sheet of paper. So think of your favorite county in your CWA or parish if you're listening from Louisiana, Cisco's Louisiana offices. And I'm going to tell you that in your favorite county, you have a convective environment parameter space classified by 1,000 joules per kilogram mixed layer CAPE, 50 knots of effective bulk shear, 300 meters squared per second squared of effective storm relativity, and we'll just go with those parameters. And a storm forms in your county, or you expect it to form in your county. What is the probability that within 2 hours into the future, that storm produces severe hail, severe wind, or a tornado? That is absolutely critical information to consider. So I want you to write down the probability. Let's go with a tornado. So we're dealing with 1,000 joules per kilogram of ML CAPE, about 50 knots effective bulk shear, and 300 effective storm relativity. Write down what you think the probability is that that storm produces a tornado within 2 hours from the future down the path of the storm. I'm going to give you guys 15 seconds to do that because that's how much time sometimes we have to be able to come up with a threat assessment. So, maybe we'll go to 10 seconds now. Fast 10 seconds. How about 5 seconds? All right, so you have a number. Now I want you to turn to the right or turn to the left or compare your numbers with other coworkers. I'm guessing you guys probably have different numbers. Some of them might be similar, but some of them might be different. Some of them might be very different. But this is absolutely critical information for which we need reproducibility based on scientific data sets in order to provide the scientific foundation for tactical threat messaging for severe thunderstorm hazards. When we talk about issuing severe thunderstorm and tornado warnings, we're addressing timescales that are very short, maybe lead times of 5 to 15 minutes, depending on the mode, the scenario, the environment. That's not enough time for some of our partners to be able to accomplish the precautionary preparedness actions that they need to take in order to protect life and property. And the convective watch scale, outlook scale, can sometimes be too broad and of too low resolution to be able to address the needs of our partners and customers. So there's a critical intervening time frame within the watch warning phases of convective events that are going to be very dependent upon the mesoscale environment that we must leverage to be able to provide the tactical threat assessment for severe thunderstorm, hail, wind, and tornado hazards. That's what SCRAM does. SCRAM, now you can stay in the room, the Statistical Severe Convective Risk Assessment Model. This is a statistical model that maps the convective environment parameter space to the probabilities of severe hail, severe wind, or tornado occurrence within 2 hours into the future. So we're able to get the environmental parameter space and the multitude of thermodynamic and kinematic parameters that go into modulating convective storm intensity in order to predict into the future a couple of hours based on large sample sizes of past data sets. Let's see how this all goes. Again, SCRAM determines the relative frequency of historical severe weather events occurring within 2 hours into the future given initial environmental parameters where cloud-to-ground lightning occurs, effectively mapping the mesoscale environment. That's going to be key to explaining the fluctuations in convective intensity and evolution to severe weather hazards. That mesoscale environment, again, it's going to be key. It's going to be governing, if you want to say, the inflow for storms, the characteristics of the shear profile in terms of how convection evolves, splits, grows, etc., in order to bound the potential hazards that present deleterious effects on life and property. So again, think about that case I gave you earlier. I gave some parameters. What's the percent of time that we get a tornado, for instance, given, now these are other parameters here, but parameters are going to vary from case to case. SCRAM will tell you those probabilities based on a reproducible, repeatable data set, very large data set, serving as the foundation. It's a system that relates current meteorological conditions via thunderstorms to short-term forecasts of severe weather probabilistically, which we can use as the foundation for threat messaging for severe thunderstorm hazards. So we start with SPC mesoanalysis data every single hour from 2006 to 2014. Pair that with cloud-to-ground lightning data sets as well as severe weather reports corresponding to downstream locations from those initial lightning grid boxes and corresponding convective environments to determine whether or not we get severe weather. So let's say, in this example, we're going to look at the Ozarks region and west of that through southwest Missouri. Let's say in this initial hour we have lightning that occurs within these grid boxes highlighted in the yellow outline over here. Within each of those grid boxes, we are going to have an associated environment, mesoscale environment parameter space. That includes the shear profile, case distributions, all the various things we look at mesoanalysis associated with those lightning strikes. It also is associated with a bunker storm motion estimation for a right-moving supercell that we can use to project forward by 1 hour into the future from these lightning grid boxes. We're effectively simulating the motion of a storm over 1 hour into the future, just like this over here. Then, within that hour duration, we are going to collect all severe storm reports that occur within a 40-kilometer radius area swept out by this circle over here to determine whether or not that storm produced any severe weather reports. Rinse and repeat. We do the same thing for the second hour into the future. We'll project, using the bunker's right-moving supercell motion technique, a downstream anticipated storm location at 2 hours in the future, and then sweep out that midway through that second hour time frame all severe storm reports in that area. Now, when we divide, and again, these are the midpoints through the first hour and the midpoints through the second hour, that we sweep out and gather all severe storm reports within the respective hours. And if there are no severe weather reports, that goes into the null data set. Severe weather reports would go into the positive, or the hits effectively. When we divide the hits by the total number, we can gain conditional probabilities for severe thunderstorm hail, tornado, and wind reports, as for severe weather, severe thunderstorm hail, and wind and tornado reports, based on dividing the hits by the total number of occurrences within each individual range of convective parameter space. By binning effectively each of the individual parameter ranges, like 0 to 249 joules per kilogram MLK, the next iteration up, we can get a smoothed out, at least to some extent, probability distribution for numerous parameters. Effectively, what is the conditional probability conditioned upon lightning occurrence and the convective environmental parameter space of severe weather report occurrence within a couple of hours into the future? This is one of the most comprehensive data sets for severe weather forecasting, with a sample size of multiple million lightning environment grid hours, by which we relate downstream severe weather reports to diagnostic parameters. This is a very big challenge. How can we relate diagnostic environmental parameter space to the potential for severe weather into the future, effectively translating diagnostic mesoscale environment to a prognostic assertion? This is very much in line with the War on Forecast and FASTS initiative. So let's talk about the science more behind these probability distributions. So I'm going to show a probability distribution, or a conditional probability distribution, for severe wind occurrences within different ranges of MLK. What this means, and that's the black curve here. Don't worry about the blue curve. It's in publications that you can see later on. What SCRAM is saying is that between 500 and 749 joules per kilogram of most unstable case, 2.6% of the time that lightning occurs in that environment, we end up getting downstream severe wind reports. And then all the times are null cases. And with increasing ranges of MLK going all the way up to 4750 joules per kilogram in most unstable case, we get upwards of 8% of the time, or a little over 8% of the time, severe wind occurs downstream. We can slice and dice the data sets in so many different ways. For weak tornadoes, significant tornadoes, based on effective bulk shear, you can see the ramp up, especially in effective bulk shear, above 40 knots of weak tornado probabilities, and then above 55 knots for significant tornado probabilities, or 50 knots or so for significant tornado probabilities. This is key information, now also from a research perspective, in terms of understanding the predictability of certain parameters for convective threat assessment, severe weather assessment. One of our findings is the muted predictability, or the lack of predictability, of LCL heights actually in tornado probability as threat assessment. And that's something you can reference in our weather and forecasting paper. We can slice and dice the data set even more. This is some powerful work that our Weather Service Topeka pathway student Ryan Bunker performed during his research experiences for undergraduates program that I mentored him, and a collective team of us mentored him through, where he looked at the subset of data across the southeast domain of the United States and embedded sub-regional coastal domain to identify the predictability of tornadoes occurring within the nocturnal periods across the southeast. This is actually a paper for which I just submitted a proof back for in weather and forecasting, so you can check out the details, but there's some really insightful things here. Whereas the entire region outside the southeast United States has a tornado probability distribution that goes like this with effective storm relative velocity, we get different levels of predictability for nocturnal tornado occurrences in the red curve over here, where we have a much steeper ramp up in the predictability in 200 to 450 meters squared per second squared or so, from a somewhat flatter distribution below that, whereas the embedded subregional coastal domain has very muted predictability. So when you kind of collapse on the subregional coastal domain, we see much less predictability in nocturnal tornadoes using effective storm relativity. We can slice and dice the data set even more in terms of the month across the United States. What we see, anecdotally, is that the predictability of significant tornadoes varies to some extent between the November to May timeframe, when we have stronger forcing for ascent accompanying mobile wave patterns be more pervasive across the CONUS, compared to the June to October timeframe, where we have weaker forcing for ascent and a potentially lower predictability scenarios for significant tornadoes. And indeed, compared to November to May, comparing June to October, we see probabilities of significant tornadoes fall by a factor of 5 to 10, actually, going from different times of the years, with little to no variability. In other words, as STP increases, that is the significant tornado parameter, the probabilities for significant tornadoes vary very little and flatline at low values in that weaker forcing for ascent time frame, highlighting the lacking predictability in June to October time frame, with much steeper incline in the probabilities for significant tornadoes at other times of year. No surprise here. This is actually a convective outlook case that I actually worked there at SPC, a very challenging case. We had multiple supercells evolving within an area of high STP from southern Wisconsin through the lower Ohio, and I should say lower Great Lakes in the Ohio Valley region, high STP value supercells evolving, and the only significant tornado of the day was outside of the core of the highest STP values here in Nickerson-Hutchinson area, Kansas, actually. That was actually a very photogenic tornado there, a very challenging forecast to say the least, and highlights that very, very challenging warm season dominated predictability of significant tornadoes. There are many explanations for this as far as why this works out. In many areas, targets of opportunity for the human forecaster to be able to infuse scientific knowledge in terms of resolving the threat assessment for significant tornadoes in the warm season. I highlight some of the if you want to say, the more SCRAM automatable predictability muted nature for significant tornadoes in the summertime, and some of the reasons here. But this is an area of much additional work to do as far as warm season, weak forcing for ascent, significant tornado predictability. This research highlights that. But that's not enough. Let's apply that. Let's apply this to operations, R2O, using the various parameters that we know as meteorologists go into describing the conceptual models that govern convective threat assessment. We're able to use a process with a fancy phrase, expert elicitation, that is where we're identifying the parameters that could go into predicting severe storms, wind, hail, and tornado, and then bin all of these parameters together using the SCRAM foundation to come up with conditional probabilities of severe hail, wind, and tornadoes. So for severe wind, we use this mishmash of various parameters over here, kinematic, thermodynamic parameters, hail, and tornado, to come up with the percent of time, given binned regimes of each of these parameters, we get wind, hail, and tornadoes. Now, this is something that is based on a lot of combined expertise, severe storms analysis, to come up with plan view depictions of both the conditional and unconditional probabilities for severe wind, hail, and tornadoes. And this is now on an online, real-time, dynamically updating website interface that forecasters across the Weather Service can look at. I've shared this with all the central region offices, and we'll be talking about this as time permits as I go to Miami as well. Thanks for joining everyone there in Miami. Really appreciate it. This is something that displays every single hour the conditional and unconditional probabilities for severe tornado, wind, and hail occurrence. So let's look over here. Let's look in central Iowa, for instance. This is in the past. You can see I have the conditional probabilities for wind are in the contour gray values here. So let's see, this is 5, 10, 15. So what this is saying is that the conditional probability, so if lightning were to occur within this environment over here, this mesoscale environment, there is a 15% of the time that goes on to produce severe wind 2 hours in the future. Think about how powerful that is in terms of having that probabilistic guidance serve as the science foundation for tactical threat messaging. The conditional nature is going to help us effectively provide that level of messaging, the innards of the messaging that are critical for actionable decision making. And so we have the conditional probabilities and all those contours over here. But are we going to have lightning occur in that area? We attempt to address that part of the problem with the unconditional probabilities, which are shown in the color fill over here. That's areas where the lightning potential from the HRRR is producing lightning output, effectively making those conditional probabilities unconditional through the depiction of lightning, where we have both the conditional environment as well as presence of lightning depicted. Now, what these individual hours do is it actually combines the remember, each individual hour will be 2 hours in the future. Then we take the maximum value within 4 hours of the future. So don't get too hung up on the values. Think of this as a 2 to 4 hour anticipation of the actual foundational probabilities for severe hazard occurrence going into the future. Each individual hour, starting with just after analysis hour, each hour 14 hours in the future to loop through. You get tornado, wind, and hail, various other attributes as well. This is very critical. So say for instance, we have a conditionally favorable environment in central Iowa, northern Illinois, probabilities of 20%. That's based on the RAP environment. Now, the HRRR is not depicting lightning, but as meteorologists, we can be looking at some of the RGBs, GOES 16 imagery, and if we expect as a meteorologist convection to occur, LFCs to be breached, some of the scenarios where CAM guidance does not resolve the solenoidal circulations, accompanying a dry line in strongly capped scenarios, in some scenarios doesn't develop convection, we expect it to occur, then we can identify a conditional threat, and then if we anticipate storms to form, we can leverage those conditional probabilities to say, well, there's some potential for storms, and if they form, there's a good chance they would produce wind over here. That's absolutely critical information. Let's show some examples. Since I'm moving to Florida, let's start with Florida. Here's a stripe of tornado probabilities here based on the mesoscale environment going a few hours in the future. As you can see, the actual mesoscale environment is characterized by kind of what I talked about at the beginning of this case. Mixed layer cape on the order of 500 to 1,000 joules per kilogram, effective bulk shear, 40 to 50 knots, effective storm elasticity of 300 to 400 meters squared per second squared. We see tornado probabilities that are going into yellows and oranges, and our experience with this model and some of the verification shows that that's showing a really, even this low cape scenario where hydrodynamic perturbation pressure gradient forces will be absolutely key to governing the potential for enhanced tornado potential. That's very highlighted from the Tampa Bay area northeastward up the coast of the Atlantic coast of eastern Florida peninsula with relatively high wind probabilities as well. So even the low cape scenarios, we are looking at the percent of time that lightning producing convection goes on in the next few hours produces severe weather. Now, where we see yellows and oranges for tornadoes, that's absolutely critical to, and greens too. Again, this is going to help us with situational awareness, where you see the greens, that's giving you awareness that there might be an issue. When we see yellows and oranges, that's increasing confidence within the next couple of hours that is an unconditional threat beginning to evolve. Now, when something like with severe winds, we already know winds are inherently associated with low predictability. Like, for instance, across South Florida, well, many different areas of convection, and only a few of them actually produce severe wind. So when we see values that are in yellows or even higher, that's an indication that we have good potential, really good potential for severe winds. That really is a very key situational awareness tool, that we have a favorable environment for a severe storm, how it varies in spatiotemporally into the future and across the area. And when we see yellow and higher values, especially for something that's inherently with low predictability, that really should be alerting us about predictable concern. Now let's go back to central region here. This is actually an upslope, moist upslope flow pattern up to the Cheyenne Ridge area to southeast Wyoming. Return flow on the west and southwest flanks of a surface anticyclone spreading across portions of the middle and lower Missouri Valley region. That moisture plume on that flank of that ridge extends northwestward into east central Wyoming in this particular case, and is associated with relatively high buoyancy values that are, and sufficient deep shear beneath, probably, I'm guessing in this case, westerly to northwesterly flow aloft to support a convective environment parameter space that's alerting us to some modest tornado potential. Here, we certainly got a string of tornado reports, and this is absolutely key to being able to get that situational awareness from the mesoscale environment to provide that tactical threat assessment that we can really hone in on very, very key high-resolution spatiotemporal precision of related hazards. Hail, really good potential. Indeed, we had hail reports over here, and wind as well, to really not only get the areas, but also the magnitude, the confidence level, etc. And this will vary hour by hour. Let's go to the northeast. You can see, as I said, wind is inherently associated with low predictability. So in order to get any probability, that's a strong alerting signal. And this is definitely a case where we got a number of wind reports. And of course, going up to some of my old stomping grounds up through Montana. Actually, I was in central Montana, Great Falls, but regardless, out in eastern Montana where they get some more tornadoes, relatively speaking, and it's northwest South Dakota, western North Dakota, very key area here for a mesoscale environment really supporting greater tornado potential, and indeed we did see a string of tornado reports there. Ultimately, in any study, and actually I want to give a more personal anecdote to a case I worked here. This is what led to the duck boat incident. It actually evolved from an elevated convective cluster that eventually rooted at the surface and grew into a forward propagating convective system spreading across portions of northeast and east central Kansas into south central Missouri with a long string of wind reports. This was a very low predictability scenario. It was the northwesterly flow aloft in a differential anticyclonic vorticity advection pattern aloft. This was low predictability. But with the middle of the speed max shoving an EML plume out over adequate low-level moisture, producing very high buoyancy, we were able to get a forward propagating convective cluster that we were getting signals, interspersed signals of yellows and oranges in the SCRAM guidance, which is giving us hints that we could be dealing with a potential severe wind episode over here, which came to fruition. So even if you see low values of wind, that's certainly an alerting tool that we need to be ready for the potential for that phenomena to occur. Now, there are going to be scenarios where we're going to get reports outside of those yellow areas, for instance, and that's going to, and we're certainly doing a lot of work to understand those environments, refine, fine-tune the model so that we can increase its ability to get those, call it sneak attacks, for lack of a better phrase, or lower predictability severe hazard episodes. Another case over here across Kansas where we had one boundary come through, dry out the boundary layer a bit, veered winds to the northwest, but still enough buoyancy because we didn't completely scare out the moisture. You can see dew points holding in the lower to middle 60s. Another boundary coming through across the Kansas-Nebraska area, coming through Beatrice right now, approaching north central Kansas near Concordia. And that was absolutely a key feature for supporting the initiation of convection that would evolve within a steeper, low-level lobstrate environment here, larger temperature dew point surface fostering ample subcloud evaporation and related microburst potential and momentum transport from the 700 millibar level down to the surface, enhancing the wind threat for a very narrow swath of wind, severe winds, even 1/6 severe, and I got to work that one. That was a very challenging case on radar, to say the least. And seeing these splotches of yellow was a key situational awareness tool. Here are some reliability diagrams showing that within the first 6 hours or so, SCRAM output is quite reliable across the board. You get more to 6 to 9 hours, and there's a bit more of a bias in some of the parameters as we get out into more extended ranges. I'll stop with a conclusion just a moment. I want to just make a big shout out. This is actually a system that SPC lead forecaster John Hart created, the SCRAM system, and brought me in many years ago now, actually, to develop all of the training and on the weather forecasting papers. We've been a team on this for years now. I'm so proud to have been working with John on this. He's an amazing friend and mentor to me, and been doing this for several years now. And it's just been awesome. This is actually a picture from right leading up to my my adjunct professor defense that I was going into at OU. John created this system and involved me on it. It's just been a true honor to be working on this. There are a couple publications already out there in weather forecasting, Hart and Cohen publications. The one from Ryan Bunker et al. Is going to be coming out very soon. And I'm going to stop with conclusions. We have 5 minutes for questions. Thank you very much.